All right, it is a little past 10, so we'll get started here. So let me just briefly at the beginning talk how the rest of this week is going to go. So today we're going to focus on the PowerPoint that I had for Monday, which is why we have April 12th up here. Then I'm going to record the PowerPoints for the 14th and the 16th. And put those into the 16th folder. So 14th, 16th lecture. We'll go in the 16th folder. So it'll probably be like part 1, part 2. This lecture, the 16th, it's really short. There's only like 2 questions on there. So that's why I'm just going to jam it into the same day. But remember the Friday, which is the 16th, no live lecture. So I'm going to record those today. You should see those up sometime today. And they'll be in the 16th folder waiting for you. So like I said, if you like watching class right at 10 a.m., they'll be there at 10 a.m. for you to continue your routine. Since I'm not going to be here for the 16th, do send me questions if they pop up during the lecture. Like if I said something, you didn't quite get it, feel free to do that. And feel free to treat it as a live lecture. Well, we're still going to have questions, and we're still going to try and solve those questions. So just pause the video when you're watching it and see if you can solve it. If not, then you can watch me do it. And if you try to pinpoint where you had a question or where you got stuck, and let me know if you need assistance with that. Otherwise, let's get into it. And for the last couple of lectures, we've been talking about quantum mechanics, and we've been talking about, orbitals and how electrons are found around the nucleus of an atom. And then we looked at, how to label the orbital diagram for any atom, the 1s2, 2s2, 2p6 business. And when we do this on the periodic table, we notice something in that elements in a column, they usually always end in the same type of configuration, right? So your noble gases, always end, except for helium. Helium's a little weird, but they always end with like 2s2, 2p6, or 3s2, 3p6, right? They always end with 8 electrons in their outermost orbital. While if we look at alkali metals, they always have 1 electron in their outermost orbital. So 2s1, 3s1, 4s1. Earth metals, they always end with 2 electrons in their outer orbital. Halogens always end with 7 electrons in their outer orbital, right? And remember, these are valence electrons that we're talking about. And the amount of valence electrons that you have, that influences how you behave in a chemical reaction. Generally, atoms want 8 electrons in valence electrons. So generally, because there are exceptions, you want 8 valence electrons. Valence, NC. And atoms will react in such a way to make sure they have 8 valence electrons. And I believe that's shown on the next slide here. So our group 1 metals, they always have 1 electron in their valence, 1 valence electron. So the easiest thing for them to do is to lose that electron, and then they'll have a full valence shell. They'll have 8 electrons in their valence shell if they lose an electron. And we learned this very early on when we were looking at our group 1 metals. In a reaction, they always form a +1 charge. Right? Our group 2 metals, they have 2 valence electrons, and the easiest way to get 8 is to actually lose these 2. All right, and let me explain that. If you're not quite getting that, what do I mean by, like, if I lose 2, I have 8, right? So let's look at the full electron configuration of magnesium, right? So magnesium is 1s2, so 1s2, 2s2, 2p6, 3s2, all right? So that is magnesium. Remember, our valence shell are the shell with the highest energy level. So our highest energy level for magnesium is 3. And we have 2 electrons in that shell. Well, let's imagine I lost those 2 electrons, right? So I got rid of those 2 electrons. Now my highest energy level is 2. And I have 2 + 6, 8 electrons in that orbital now. So magnesium's happy. That's why these metals always lose 2 electrons and become +2 cations. Remember, cations are positive. Cations in reactions. The goal of most molecules is to have the electron configuration of their nearest noble gas. So if we look at the halogens, so the electron configuration for fluorine is 1s2, 2s2, 2p5, right? It has 7 electrons, 7 valence electrons. So to get 8 to become this noble gas, it only needs 1 more electron. That's why your halogens always become -1 in a reaction, because they gain 1 more electron. So at 2p5, they go to 2p6. They have a full, what's called an octet. If you took high school chemistry, you might remember the phrase octet. As a full octet, and now it's happy. Same thing with these elements, the column that oxygen is in. They, for example, oxygen has 1s2, 2s2, 2p4, so it needs 2 more electrons to become 8. Right, so we can understand a lot of why molecules behave the way they do if we realize we're trying to get to a full octet. Your transition metals, though, they are a little bit weird and they don't quite follow that. But any questions about that? Excuse me, I needed to sneeze there. But any questions about the concepts we're talking about? All right. So what I want you to do is, I have a bunch of ions here. I just want you to write out the full electron configuration like we did on Monday. So I'll just do oxygen here, so you get the gist of it. So I'm doing oxygen 2-, right? So normally oxygen is 1s2, 2s2, then 2p1, 2, 3, 4. That's neutral oxygen, but it's oxygen 2-. So that means I have 2 extra electrons. So instead of 2p4, this would be 2p6, which is the same electron configuration as neon. So I want you to try and figure that out. for the rest of the elements, feel free to use the shorthand notation we learned on Monday, where you can just put in the nearest noble gas instead of writing out all the 1s2, 2s2 stuff. But I'll give you a couple minutes to do that. If you have questions, let me know. All right, let's start taking a look at these. A, B, and C are relatively straightforward. D and E are going to be the difficult ones because it's something I haven't told you yet. But let's look at B. So bromium minus. So the noble gas that comes before bromium is argon. So we can just do our shorthand. Argon, then we're on the fourth row here. So that's 4s2. Now remember, when we get to the D block, it's row -1. So this would be 3D, and then there's 10 of them, so 3D10. Then normally it would end up at 4p5, but since we have one more electron, that's 4p6. SR2 plus, the noble gas before SR is krypton. And normally SR is krypton 5s2, but we lose 2 electrons. So it's just krypton. So you could actually do it like that. All right, cobalt. This is the tricky one, one of the tricky ones. So I'm going to write neutral cobalt down here. So the noble gas before cobalt is argon. So argon, then 4s2, then 1, 2, 3, 4, 5, 6, 7. Cobalt is the 7th D block element. So that's 3d7. Now I'm losing 3 electrons, right? And when you lose electrons, you lose them from your valence shell first. And here, for cobalt, our valence shell is the 4th energy level. So we're going to lose 2 electrons from our highest energy level first. So 4s2 will go away. Then we're going to lose 1 electron from the 3d orbital. So cobalt 3 plus is argon 3d6. 2 electrons came from 4s. 1 electron came from 3d. And it's the same idea with copper 2 plus. So copper, neutral copper, is argon. And it's the 9th element in 3D. So it's 4s2, 3d9. Copper 2 plus means we lose 2 electrons. So they're going to come from our valence orbital shell, which is 4s. So this is argon 3d9. So questions about electron configurations for ions. All right, if not, we can move on then. And if you're still typing, feel free to continue to type out. All right, let's talk about magnetism now. Why are some things magnetic and some things not? It has to do with electrons and whether you have paired electrons or not. So if you remember our electron diagram here, where each arrow is an electron, and for each value of m sub L, we get to put 2 electrons, but they have to be facing in different directions. And you remember this is our quantum number called m sub s, which is spin. And they have values of plus 1/2 or minus 1/2. So spin up or spin down. And when you do an electron diagram orbital, if you have electrons that are in a m sub L slot all by themselves, that is, they're not paired, that makes your material magnetic. And the word for that is paramagnetic. However, if I was to pair up everything, then these paired electrons would not be magnetic. Everything's paired up, so this element, this element would not be magnetic, so that's diamagnetic. So that is what is determining whether something is magnetic or not. Do you have unpaired electrons in your orbital shells? If yes, you're magnetic. If not, you're not magnetic. So we're going to figure out, based on orbital diagrams, whether we're magnetic, diamagnetic, which is not magnetic, or paramagnetic, which is yes, you're magnetic. Right? So let's do V5 plus. So I need to get out my periodic table. which I always keep handy on my desk. And let's do the neutral version of V. So that's element number 23. And it has the electron configuration of argon. Then it would be 4s2, 3d5. Or sorry, 3d3. So that's neutral V. And since I'm going to take away 5 electrons, let me write it in a different way that's equivalent. Another way I could write this is neon, 3s2, 3p6, 4s2, 3d3. And now I'm going to take away 5 electrons because it's plus 5. So I lose 2 electrons from my outermost shell, which is the 4th energy level. So 2 electrons from 4s2. Then I lose it from the d orbital, so 3d3. I lose 3 electrons there. That's a total of 5. And my electron configuration then is neon 3s2, 3p6. So let me write out my orbital diagram here for 3s2, 3p6. Oops. So just as a reminder, the s orbital, that's when L is 0. So you only have 1 m sub L value, so 1 dash. The p orbital, that's L is 1. So your m sub L values, you have 3. So you get 3 dashes. And then your d orbital, L is 2. So m sub L could be -2, -1, 0, 1, or 2. So you get 5 dashes. That's how we decide the dashes again. So it can't just be AR. It can just be AR. The reason why I'm doing this, where I have neon, is just to show you what the outermost valence electrons look like. It's just for an exercise purpose. Because if I just had AR, it might not be obvious to everyone what the outermost shell is, which is the 3rd energy level. So I'm just showing that. So if we look at this, I have my outermost shell is 3. I have 2 electrons in 3s orbital. So they have to be paired because there's only 1 m sub L value. I have 6 electrons in my p orbital. So 1, 2, 3, 4, 5, 6. In my outermost shell, everything is paired up. Since everything's paired up, this is diamagnetic. This is not magnetic because I do not have a free electron. Every electron has a partner. So that's our goal here. I want you to try to do B, C, D, and E and tell me, are these magnetic or are they not magnetic? So I'll give people a couple minutes to do this. If you have questions, feel free to let me know. Can you do one more? I'm still lost. Okay, I can do chromium 3+. That's no problem. So chromium. So the way I do this is you always start with the neutral atom. So let's do chromium neutral, right? Chromium element 24. So it has the electron configuration of argon, 4s2, then 1, 2, 3, 4. It's the 4th element in the D block. So element 24. 4s2, 3d4. So let's do our orbital diagram just for neutral chromium, right? So the S block gets 1 dash because it has 1 m⁴ value. The D block gets 5 dashes because m⁴ has 5 different values for D because L is 2. So neutral chromium, I put 2 electrons in there because it's 4s2. And for neutral chromium, I put 4 electrons in the D block. And remember, one of our rules is when we're putting electrons in an orbital, they do not want to be paired up if they don't have to be. So I have 5 spots where an electron could go and only 4 electrons. So each electron gets its own spot. So for neutral chromium, I have unpaired electrons in the d orbital. They don't have a partner in their slot. So neutral chromium is magnetic. So we would call that paired magnetic. However, the question is for chromium 3+. So 3+ means I lose 3 electrons. When you take electrons away, you always start with the highest energy level first. The highest energy level is the 4s orbital. So I take away 2 electrons from there. So this actually becomes 4s0 because I took 2 electrons from there. Then I take 1 electron from the 3d orbital to make that 3d3 instead of 3d4. And let's update our orbital diagram. So I have nothing in the 4s orbital anymore because I took those away. Then I took away 1 electron in the d orbital because I'm 3d3. However, you see chromium still has unpaired electrons. It has 3 unpaired electrons in the d orbital. So chromium 3+ is still paramagnetic because I have unpaired electrons. Did seeing it for the second time help a little bit? Okay, good to hear. So try to do nickel, iron, and cadmium. In case you can't find these on the periodic table, nickel is element 28. Iron is 26, and cadmium is element 48. Right, so I'll give you a couple minutes to see if you can get this, and then I'll be back. So I'm confused on how you know how many spaces you have for each orbital. Like, how do you know for 4s there's one space to put? That's what I was doing down here, right? So the s orbital, remember the s orbital means L is 0. And based on our rules, if L is 0, m sub L has exactly one value, 0, because the limits for m sub L. So let me just do this. When L is 0, that's called an s orbital. When L is 1, that's called a p orbital. When L is 2, that's called a d orbital, right? And our rules for m sub L is that the values of m sub L depend on L. And they range from minus L, 0, you always include 0, to plus L. Right? They go from minus L to plus L, including 0. So if L is 0, your only value of m sub L is 0, so you get 1 dash. If L is 1, you have 3 possible values of m sub L. Minus 1, 0, 1. So you get 3 dashes. When L is 2, you have 5 possible values of m sub L. Minus 2, minus 1, 0, 1, 2. So you get 5 dashes. That's where the dashes are coming from. All right, so let's take a look at this. Let's do nickel 2+. So the way I like to do this to show people how it's done is I always write out the neutral element and then do the ion. You don't have to do that. You can just go straight to the ion if you're feeling confident. But nickel itself is argon, 4s2. Then it's 1, 2, 3, 4, 5, 6, 7, 8. The 8th element, 3d8. If we're 2+, we take them from the highest energy level, which is the 4th shell. So we take 2 electrons there. And we're left with 3d8. So the d orbital has 5 spots, right? So 1, 2, 3, 4, 5. And we put in 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. We still have 2 unpaired electrons. So that would make it magnetic. So it's paired magnetic. Let me erase some of this nonsense. Right, so let's go to iron 3+. So iron by itself, argon, then it is 4s2, 1, 2, 3, 4, 5, 6, 3d6. And I'm going to make it 3+, so I'm going to lose 3 electrons. I take 2 from the 4s2 orbital. And I take 1 from the 3d orbitals to make it 3d5. So iron 3+ is argon 3d5. D orbital has 5 spots. 1, 2, 3, 4, 5. Remember, electrons want to be alone if they can. So your 5 electrons should not be paired up. So that's paired magnetic. So to be diamagnetic, all have to be paired. Yes. If you have 1 unpaired electron, you are magnetic. Okay, cadmium 2+, which is element 48. So the noble gas before cadmium is krypton. So we can do krypton. Then it would be 5s2. 4d, and it's the 10th element, so 4d10. It's the 10th element in the D block. 2 plus, so we lose 2 electrons from the 5s orbital because it's our highest number. So we're 4010 for cadmium 2 plus. We write out our d orbital. We have 5 dashes, so this is 4d. And then it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everything's paired up, so that is not magnetic. So that is diamagnetic. All right, so that's how you can determine, based on orbital diagrams, whether something is magnetic or not. Questions about that? All right. There's no questions. We can move on. And the next thing we're going to talk about is size of atoms. And the thing that determines how big an atom is the distance from the nucleus to their valence electrons. So the bigger the energy level valence electrons you have, the bigger the atom, right? So an atom that has electrons in the 4s shell is smaller than electrons that have it in the 5s shell. So when we're talking about size of neutral molecules, that's very important. These are neutral molecules because it changes when we have ions, but this is neutral molecules. Generally, as you go top to bottom, you get bigger. And I don't know why this slide has it reversed, but I'm going to do, as you go from right to left, you increase as well. So your biggest element is rubidium. And your smallest is helium. Now, there are exceptions to this, but in general, as you go from down and to the left, for neutral molecules, atoms get bigger. So just remember that. Down to the left, neutral molecules become bigger. So here we just have a bunch of atoms, a bunch of like or statements, and using your periodic table based on what we just said, I want you to determine what is bigger, what is the biggest. And let me just copy over the periodic table so we can all be looking at it at the same time here. This, pop it over here. Okay, let me share that again. Screen with this. All right, so here's the periodic table. So for A, I'm seeing what's bigger, aluminum or indium. Well, remember, down and to the left is bigger, so indium is the biggest. So using your periodic table, figure out B, C, D, and E. Then F, just put them in order for me. And for what I'm going to do for F to make it easier while you work on B, C, D, and E, I'm just going to start like labeling these elements so I can find them easier for F. CA, RB, S. So there's all the F elements. All right, so let's knock these out. Not too complicated here. So silicon versus nitrogen. Well, silicon is down to the left of nitrogen, so silicon is bigger. Phosphorus versus lead. So phosphorus 15, lead's 82. So lead is way bigger than phosphorus. Carbon versus fluorine. Well, carbon is to the left of fluorine, so it's bigger. And tin, which is SN right here, versus silicon. Tin is below silicon, so tin is bigger. Then arrange these elements from small to big. So all you're doing is working from the top right to the bottom left. So fluorine is the smallest, then sulfur, silicon, germanium, calcium, rubidium. It's just from top right to bottom left, small to big. Right. Any questions about how to determine what is the larger atom using the periodic table? Larger neutral atom. Right. Now let's talk about cations. And generally, when you become a cation, you become smaller because you lose your valence shell and you form a new valence shell that's lower in energy level. So a cation just sheds its outermost electrons. And when it does that, it shrinks. While anions, they gain electrons in their outermost shell. And anions are negative, right? So electrons want to push away from each other. So when you gain electrons, you become bigger. So just to summarize that, cation you shrink because you lose electrons. Anion, you grow because you gain electrons. Do you keep saying neutral because there's a different rule for not neutral molecules? Indeed, there is. And it's right here. If you're a cation, you shrink. If you're an anion, you grow. So I think, yeah, this is the last slide. So just tell me, based on this, what's the larger species? So A, I'll do that. I'll do A and B because B is interesting, right? So A, we have a neutral molecule versus cation. Well, when you become a cation, you shrink. So lithium's bigger. All right, let's look at I minus and CS plus. Now I is element 53, CS is element 55. When I get an electron, it gets the electron configuration of Xeon, right? Gets one more electron and becomes Xeon. When CS loses an electron, it also gets the electron configuration of Xeon, right? And you can look this, you can confirm this by doing what we did previously today, where we figured out what is the new electron configuration of atoms when they're ions. But they both are Xeon. The difference here is that iodine's negative charge and CS is positive charge. So the rule is, if you have the same electron configuration, the more negative you are, the bigger you are. So same elect config, more negative equals bigger. So that's one caveat here. Let me just do C, D, and E because we're out of time here, and C, D, and E are not complicated, right? Chromium versus chromium 3, C 3 plus, right? I became positive, so I shrank, so chromium is bigger. Oxygen versus oxygen 2 minus. Well, I became negative. When you become negative, you become bigger. Nitrogen versus nitrogen 3 minus. Well, I became negative, so I'm bigger. And F. F, I'm talking about what's called an isoelectronic series. That's a fancy way to say the same electronic configuration. So what I'm saying is these 4 atoms are just like the example in B, in that they all have the same electronic configuration. These all have the electron configuration of krypton. All of these are equal to krypton here. So I want to know what's the size from small to big. And the more negative you are, the bigger you are. And the more positive you are, the smaller you are. And this holds for isoelectronic. All right. So if you have the same electron configuration, if you're comparing different atoms that are isoelectronic, the negative ones are bigger, the positive ones are smaller. So arranging this from small to big, you just arrange them in order of charge. So SR2 plus is your smallest, Se2 minus is your biggest. And that is how the size of ions change. One interesting thing about that is when we're looking at NaCl, right? Normally, if it was just neutral molecules, based on what we talked about, sodium should be bigger. But since these aren't in a reaction, what actually happened is that Na became positive and Cl is negative because it's an ionic interaction, right? So chlorine and sodium chloride is much bigger than sodium. Like when you see images of this on the internet, like that would be sodium, like that would be chlorine. Like chlorine is massive compared to sodium. And it's all due to the outermost orbital. But with that, are there any questions about our sizing here? Right. If not, we'll leave it at that. Sorry for going a little over there. I'll put a homework up. Remember, don't come here on Friday. Just go to course content. You'll find the lectures videos there. Otherwise, have a good day.